In the first part of this video lecture, we saw examples where we can lose mass in the limit. So here's a green region that is getting stretched in this direction, or a red region which is being pushed in this direction. And even though these regions, they always have mass equal to 1, we don't see that mass in the limit. That mass is escaping to infinity in some sense. Then we saw that this cannot happen if these functions were, or the graph of these functions that we have here, they were subsets of each other, they were increasing. So functions, if a sequence of functions is increasing or non-decreasing, then this cannot happen, and the integral of the function that you see in the limit, it will respect, and it will be the limit of the integral we see before. And now we move to a more general case where we don't make any assumptions, and when we don't make any assumptions, we have to give up something, of course. And this is Fatou's lemma. It makes no assumptions about the functions whatsoever, besides them being non-negative. They don't need to converge, they don't need to be bounded by something, they don't need to be increasing. And what Fatou's lemma is saying is that we can lose mass in the limit, but we can never get mass in the limit. So here is the function that we have in the limit. The total mass, it can be smaller, but it cannot be larger, okay, of the mass that we have for each function. But this result is so general that it doesn't even require the functions to converge or anything. We can just take the lim here. And you see this lemma, it is consistent with the examples we saw before, where the integral of the function that we get in the limit, it was smaller than the integral of each function that we had on the way. And this is, of course, a very good way to remember, speaking a bit in kindergarten language, to remember in which direction this equality should point. Well, just think of the previous examples where we lose mass in the limit, which means the integral of the limiting function can be smaller than the limit of the functions that we have on the way. You'll see there is a typo in the upcoming proof. This n here should have been a k. So in this expression, k is a dummy variable. So you use it to compute the infimum, and the free variable is n, which is indicated in the gn of omega. So this n here should be k. So let us prove this Fatou's lemma. So let's define gn of omega to be the infimum, after n for all k larger than n of fn of omega. And let's define g of omega to be the limit, the liminf, when n tends to infinity of fn of omega. And what I'm going to claim now, and this has nothing to do with measure theory, this is a property of functions, this is a property of the liminf. What is the liminf? Well, the liminf, it really is the limit of the inf. In some sense, we can take, if we put the limit here, which means we put the limit here, what we get is the liminf. And that is to say, and the infimum here, as we increase n, we are taking the infimum over a smaller and smaller family of functions. So this is increasing as well. So what we have is gn increases to g. And moreover, since we assume all these functions are non-negative, gn is non-negative. So you will remember from the previous part of this video lecture, what can we do when we see this? Well, of course, what we can do is we can say the integral of gn increases to the integral of g. And what is the integral of g? Well, what is g? G is the limit, so the integral of g is exactly what we have on this side of the equation. So now we just need to do something smart with this side of the inequality to see what we can show. And to do that, what we need is to observe the following. Gn is bounded from above by Fn. And how that? Well, it is the infimum of a collection of functions which include, in particular, Fn. So therefore, it is smaller than Fn. And because of this, well, we can integrate. And since now this inequality holds for every n, we can take the liminf on both sides. Just did some magic here. So we can take the liminf at n tends to infinity on both sides. Well, the liminf on the right is not really a liminf because we already know the integral of Gn, it converges to something. And it converges to what? It converges, we said already, it converges exactly to this. And what is the liminf of Fn? Well, that is exactly what is here. And this will conclude the proof of Fatou's lemma.